Welcome to this video where we will discuss the epsilon-delta criterion for continuous functions and then formalize them in the proof solver Lean4. With Lean, we are able to code our proof in a programming language. This forces us to think rigorously about every single step. Once complete, we can be sure that our proof is 100% correct. There's a reason that continuous functions are taught at the very beginning of your math studies. It belongs to the tools of the trade and you will use it all the time in math. For example, in algebraic topology, you might consider homotopy of path. That is, you have a path and then you can apply a continuous transformation to get another path. And it's not just jumping around, no, it's continuous. And besides this homotopy of path, you might have also heard about homeomorphisms. For example, you can show that you can continuously transform a coffee mug into a donut. And when you want to write down the definition of a homeomorphism, you also use continuous functions for that. So in this video, we will discuss the epsilon-delta criterion as definition for the continuous functions, then give some examples and formalize them in Lean, and we will show that the constant function and the line is continuous, and then talk about left and right continuity. Without further ado, let's get started with the definition of a continuous function. So we deal with a function f from its domain D as a subspace of the real numbers to the real numbers. And we call that function continuous at the point A, and that point A is from the domain, if for all epsilon, for all positive epsilon, there exists a positive delta, such that for every x in the domain, whenever the absolute value of x minus a is smaller than delta, then the absolute value of f of x minus f of a is smaller than epsilon. And if f is continuous at every point in the domain D, then we say that f is continuous on D. As this is a bit technical, let's consider an example. So we have a function f here from its domain D to the real numbers, and we consider a point A. And now I claim that f is continuous at A. So you can give me any epsilon, because the definition says it holds true for all epsilon. So give me any positive epsilon, and then I say, well, there is a delta, a positive delta, such that for every x in the domain, whenever x is less than delta away from A, so this is the case here, but not here, for example, then the distance between f of x and f of A, that's the purple line here, is smaller than epsilon. For example, this is also the case here and here as well. Now, if I claim that f is continuous at every point in the domain D, I have to show it for every point A. So, for example, consider another point, and then update the values here. And as you can see, oops, our purple line here is way bigger than epsilon. But that's not a problem, because for another point A, I am allowed to choose another delta. And in this case, I just shrink down delta such that it works. Now you can see the purple line is also smaller than epsilon. Now let's see how we can formalize this in Lean. That's a programming language and theorem prover. So we just write down the definition is continuous at. We give it a set, a subset of the real numbers, and we give it a function from D to R. And then A, which is a point in D, and the type of this definition is a proposition. So we just write down for all epsilon bigger than 0 and so on. And it's basically just the mathematical definition mirrored in computer code, such that we can teach the computer what a continuous function really is. And then for the definition of a continuous function on the whole set, we just tell it, okay, well, for all A in its domain, f has to be continuous at that point A. Great, so we've discussed what continuous functions are. Let's see some examples now. In Lean4, we formalize that the following functions are continuous on the real numbers. So our theorem is as follows. Let f be a function given by f of x is c, where c is a real number. That is, f is a constant function. Then, my claim is that f is continuous at every point A of the real numbers. Let's prove that with the help of the epsilon-delta criterion. So let A be a real number, and let epsilon be a positive number. Then there exists a delta, so we can choose that delta however we like, and you will see why 1 makes sense. And that delta has to be bigger than 0, well, 1 is bigger than 0. Then for all x, so let x be a real number. Then let's see what happens if we consider the difference between f of x and f of a and the absolute value of that. We just plug in the definition of our function, which is just a constant function, so we get c minus c, which is absolute value of 0, which is 0. And then 0 is smaller than epsilon by assumption. So indeed the absolute value of f of x minus f of a is smaller than epsilon. So the conclusion here is true irregardless of the premise, which is why we can put in anything we want here and it's still true, and therefore f is continuous at a. We've shown a proof using the definition of continuous functions. Now how does this work in Lean? Well, we declare a theorem, constant function is continuous at a point. We give it all the variables we need, for example the constant c, and then we claim that this function is continuous. Down in the bottom here, I write down the goal that we have to solve. Right now we have to solve is continuous at d, the function x to c. In order to plug in our definition, we use dsimp, and now we really see what we have to prove. So for all epsilon bigger than 0, to get rid of that, we use intro epsilon. That's the same thing as saying let epsilon be bigger than 0 in a handwritten proof. And then h epsilon bigger 0 is just the hypothesis that epsilon is bigger than 0. So when we go down here, we get rid of the first part. Next, we choose a delta, so we use exists1 for that. And then we have to prove 1 bigger than 0. Well, to do that, we simplify using 1 is positive. And whenever we have true and, we can just get rid of that as well. Great, next, we introduce the variable x and the hypothesis that x is distance less than delta away from a. And in this case, delta is 1. And last but not least, we have to show that the absolute value of c minus c is smaller than epsilon. Let's do that. We simplify using sub-self, and then absolute 0, that is the absolute value of 0 is just 0. And there we go. Last thing to do is prove that 0 is smaller than epsilon. Well, that's by assumption, so we just plug in our hypothesis that epsilon is bigger than 0. Great, so nothing to do anymore here, and we are done. We've proven that the constant function is continuous at any point a, and therefore it is continuous on its whole domain. Next example is a line. So our claim now is that if f is a function given by m times x plus y naught, where m and y naught are real numbers, then f is continuous at every point a. For this proof, we have to consider two cases, where the slope is 0 or where it's different to 0. For that, we can use the by cases tactic in Lean. Again, we remind ourselves of the definition of a continuous function, and then let's get started. So in the first case where m is 0, then our function is just a constant function with the offset given by y naught, and we can reduce that to the facts that we've already shown, namely that any constant function is continuous. Okay, one step at a time. We have to show now that this function here is continuous. What we can do now is plug in the m, so we substitute m for 0, and then use the fact that 0 times x is just 0, and then 0 plus y is just y naught. Then f of x is a constant function. We have shown that constant functions are continuous, and therefore we are done with this case. We just use exact and then plug in the theorem that we've already proven. Great, so this is the case m is 0. Now to the case where m is different to 0. Again, let epsilon be bigger than 0, and now we choose this delta to be epsilon divided by the magnitude of m. I mean, you can choose any definition for delta, you just have to make sure that the proof works in the end, and you will see with this definition it works. Let epsilon and all the stuff, you've already seen that, we introduce that, and then we define delta to be epsilon divided by the magnitude of m, and we use that delta now. Since epsilon is positive, and the absolute value is by definition positive, we know that delta is positive. We need that, because we have to make sure that the delta we choose is positive indeed. And in Lean we claim this as well. We say that delta is positive, and we prove that by positivity. So with this we don't even have to write down that epsilon is bigger than 0 and so on. Lean will do it for us. It will search for tactics that it can use to prove that delta is bigger than 0. And then we simplify using this fact, and there we are again. We let x be a real number, and the absolute value of x minus a is smaller than delta. That's our premise. So let's declare that in Lean by intro, and then simplify our expression, because right now you can see in the bottom left here that y naught minus y naught is 0. So let's get rid of that. On to the main part, which is to prove that the absolute value of m times x minus m times a is smaller than epsilon. To achieve this in Lean, we make use of the calculate block. I think it's really nice because it resembles a handwritten proof. So let's see how it works. we claim that this expression is the same as m times x minus a in parentheses. Well, that's just distributivity, and luckily enough we don't have to show this by hand. Instead we use ring NF, which just uses some theorems from the ring we're working in, namely the real numbers. Okay, next line. We show that we can just split on the multiplication sign by using absolute mul. And now you can see that we have the absolute value of x minus a there. So now let's use the fact that it's less than delta. But to use that, we first have to use the theorem mul LT mul left. So the naming conventions in Lean are what they are. We just have to deal with them. And why do we have to use this theorem? Well, we don't only have this x minus a here, we also have this times m in front of it. So we use the fact that whenever a times b is smaller than a times c, then that's the same as b is smaller than c. And then you might ask, well, how do you come up with these theorems? How do you know which ones to use? Well, there's a nice website called Moogle.ai, and you can search for names or for things that you want to prove. For example, here we search for a times b smaller than a times c, and what we get is a second search result already our theorem that we want to use. Okay, so we use that fact now and plug it in. So we have is smaller than absolute value of m times delta. Now we can drop in our definition of delta, which is epsilon divided by the absolute value of m. And we just do that by reflexivity. The tactic is called RFL. And well, now you see why we've chosen delta to be this exact expression, because now the absolute value of m is cancelling each other out, and what we're left with is epsilon. And the last step is proven by field simp. The real numbers are also a special ring called a field, so we can use field simplification. And Lean does it for us. Great, so now we have smaller than epsilon, and we're done with the proof. We've shown that functions in the form m times x plus y naught are continuous at any point a in their domain. We've also formalized that the functions x squared and 1 over x are continuous on their domains, and you can see the proofs on GitHub if you want to. Last but not least, there's also the notion of left and right continuity. That's basically the same as continuity, but we say a function is left continuous when we only consider points x smaller than a. That is, we approach from the left side to our point where we want to consider the continuity. As an example, let's discuss the Heaviside function theta from the real numbers to 0 or 1, which is defined as 0 whenever x is smaller than 0, and 1 whenever x is bigger or equal to 0. To write it down in Lean, we use an if-then-else statement. We might ask ourselves if this function is continuous at the point x being 0. For the moment, let's discuss left and right continuity. For left continuity, we approach the point 0 from the left. And what we see is that at the point we have a big jump. Visually, it's not continuous here. But when we approach from the right side, we see that, well, the function value is 1 all the time, even at the point 0 itself. Theta of x is right continuous, but not left continuous. Well, that's not a rigorous proof, but for now the visuals will be sufficient for us. But the question is still, is that function now continuous at x, given that it's not left continuous but right continuous? Well, we can use a theorem for that tells us a function f is continuous at a point a if and only if it is both left continuous and right continuous at that point. In our case, the Heaviside function is not left continuous, so then we know, well, it's not continuous either. In order to prove this theorem, we have to provide a proof for both implications. Let's start with the first one. Assume that f is continuous at a. This implies both left and right continuity at a, because x less than a and x greater than a, those are just stronger conditions than x just being an element of D. So it follows kind of trivially, but in Lean still we have to write it down very rigorously. In Lean, in order to first prove the one implication then the other, we use the keyword constructor. And with this we can now prove that the left side implies the right side. First we introduce the hypothesis that our function is continuous. And then for the this implies both left and right continuity part, we split up again because first we show left and then right continuity. For left continuity, first we introduce the epsilon, and then we obtain the delta because we know that f is continuous, so there exists a positive delta, and we can use obtain to get that delta, and we use it. We use the hypothesis that it's bigger than 0, and then we introduce x as always. And last but not least, we use exact and plug in our x delta criterion. For the right continuity, it's basically the same, so I won't show it here. And then the other implication. That is, now we assume that f is both left and right continuous at a, and we want to show that f is continuous. So let epsilon be bigger than 0. Since f is both left and right continuous at a, we know that there exists a delta 1 and a delta 2 such that all the rest of the definition applies. We use obtain again here to obtain the delta 1 and the delta 2 from that definition. Next, we choose our delta to be the minimum of delta 1 and delta 2, and you will see why in a minute. Then again, we introduce x and assume that x is less than delta away from a. And now, due to our choice of delta, we also know that x minus a and the absolute value of that is smaller than delta 1, and it's also smaller than delta 2, because delta was chosen as the minimum of delta 1 and delta 2. We consider 3 cases now. If x less than a, then the distance between f of x and f of a is less than epsilon by left continuity. We can do exactly that in Lean. We use by cases. And for the first case where x less than a, we use our left continuity. Then we have the case x being equal to a. Then our function values, well, they don't differ because they are just the same. So we have 0, and 0 is less than epsilon by assumption. So let's do that now in Lean. We consider the case x greater or equal to a, and then inside that case, another case where now x is equal to a. For this case, we just rewrite and then simplify using our hypothesis that epsilon is bigger 0. And for the last case where x is greater than a, we have that the absolute value of f of x minus f of a is smaller than epsilon by right continuity. In Lean, this part is a bit longer because we're still in the case where x is greater or equal to a, but we don't want the case x equal to a. We've already done that. So we have to show that x is greater than a. And don't worry if you don't understand every single step here. It's just for a demonstration so that you see the overall picture. We can use by cases, we can use the constructor. And if you want to, you can still dive in deeper on GitHub and look into the code and then work it out for your own. Awesome, this concludes our proof that continuity is basically just left and right continuity combined. In summary, we've learned the epsilon-delta criterion for continuous functions, we've seen some examples, and then also discussed left and right continuity. Last but not least, some comments that might be helpful when you work with Lean. First, it's really helpful to work out any proof by hand first, be it in a LaTeX document or on a piece of paper. Because it might be really easy to get lost in the Lean proof and get stuck at some parts, and then it's a bit frustrating if you can't move on. And you first have to understand the overall picture. What do you want to prove? How does the proof work? What's the outline of the proof? And then you can try to formalize that in Lean. This formalization can even reveal some mistakes. For example, somewhere we forgot for all epsilon greater than 0. Or inequalities, that's a big one. We often mix up inequality with strict inequality. And then in Lean we realize, well, it's not working because we need strict inequality here. Or we can't have strict inequality and only have smaller than or equal to. And then you also make some silly mistakes, and Lean can help you with that as well. Furthermore, Lean has a really nice VS Code integration where you can interactively solve the goal. The goal will always update wherever you set the cursor in the document. And that's really powerful because you know exactly what you have to prove at each step. The parser for Lean files could be a bit more stable locally wise. That is, if you have one error in the file, it shouldn't affect other parts of the document. That's not always the case. So if you're working at multiple places in the document, maybe comment out the rest such that the parser works more stably. And then there are tons of tactics to ease formalization. Some favorites include simp, rewrite, use, lin arithmetic, ring normalization, field simplification, by cases, split ifs, and there are so many more. And then artificial intelligence might be really useful here, for example Moogle.ai where you can search for theorems, and also GitHub Copilot with a direct VS Code integration. For Lean files, Copilot is not that useful because it often suggests things that only worked in Lean 3 but not in Lean 4, and most of the time the lines that it suggests, they just don't work. But it's a great source of inspiration. It may suggest you something that you've never seen before, for example a new tactic, and then you can search in the documentation for that tactic. So for these cases, GitHub Copilot is really cool. And then of course, if you have existing Lean code, you can just select some lines and then ask it what these lines are doing. Thank you very much for listening. This was my first time working with Lean, so if you have any comments or suggestions on how to improve, then feel free to drop a comment down below. As a final note, you can become the next contributor, because Lean is open source and also Mathlib is open source on GitHub. Mathlib, that's the math library of Lean4 by the Lean-prover community. Feel free to dive into their code, and if you think that an important theorem is missing, and there will be, because Mathlib is not complete, there's so much math in the world that is not formalized yet, then you can open an issue on GitHub or create a pull request with your code, and maybe you can become the next contributor to this great project. Thank you very much and see you next time.